Hi, everyone. I hope you're feeling good after lunch. Thank you for joining us in this session, Securing Enterprise Big Data Workloads on AWS. My name is Motaz Anani. I'm a solutions architect, and I'm happy to be with you today. I am also joined by Nate Simmons, who is the principal architect at NASDAQ. Now, let me start by saying that enterprise data warehousing is still very relevant and alive today. And there's no better evidence to that than what we see in the field. Companies keep pouring terabytes upon terabytes of data into their traditional on-premises data warehouses, and they often keep doing so until they reach the breaking point of traditional technology and cross into the realm of big data. And when that happens, companies turn to the cloud for a scalable solution that can handle their data growth for years to come. And that solution is the hybrid enterprise data warehouse, where part of the data warehouse is on premises, and the other part is in the AWS cloud. But just as companies start making this transition, and after a lot of enthusiasm have been built, security often comes in as a reality check. Questions come up such as, what are the security controls that are available for us in the hybrid enterprise data warehouse? Will we be able to maintain or improve our security posture as we make this transition? This session aims to help you answer these questions and more. And to that end, I'm going to show you what a typical hybrid enterprise data warehouse looks like. I'm going to take you in a walkthrough of its architecture and its data flows. And then we are going to apply security controls across this hybrid enterprise data warehouse. And finally, we are saving the best for last. Nate is going to share with you how hybrid enterprise data warehouse security is actually done at NASDAQ. In order for this session to live up to its promise, it has been designed to be high-level enough and broad in its coverage of relevant AWS services, such that it helps you put together an effective information security plan for your hybrid enterprise data warehouse. That said, this session must be supplemented with diligent information security planning that starts with active thinking and brainstorming of the relevant risks and threats, and end with a justified and concise list of security controls that you must implement. Now, let us take a look at the hybrid enterprise data warehouse. This is a high-level conceptual architecture. On the right-hand side, there is your AWS environment in which you would leverage services such as Amazon S3, Amazon EMR, and Amazon Redshift to store, process, and analyze your data. Amazon S3 offers you a highly durable object store with virtually unlimited scalability. You can store as much data as you want. Amazon EMR is a cluster management platform that simplifies running big data frameworks such as Apache Hadoop and Apache Spark. And Amazon Redshift is a petabyte-scale relational database management and querying system that has been designed for business intelligence workloads. Now, on the left-hand side, you have your on-premises environment in which your various enterprise data sources reside, such as your database servers, file shares, and FTP servers, and from which your different end-user groups would access their data in AWS. And because we are talking about a hybrid data warehouse, that means potentially up to a few hundreds of gigabytes of data exchanged daily between both environments. In order to support that, both environments should be connected via an AWS Direct Connect, which provides you with up to 10 gigabits per second of direct physical connectivity from your on-premises networking equipment and into your AWS environment. Now, let's take a look at the data flows. The first data flow is the extract, upload, and transform data flow. In this data flow, your data engineers would set up automated tasks and agents that would extract data from your enterprise data sources and then upload this data into Amazon S3. Once your data is in Amazon S3, your data engineers would usually want to apply transformations to make the data suitable for two more purposes. The first purpose is further exploration, analysis, and manipulation by your data scientists using the Hadoop ecosystem of tools on Amazon EMR. And the second purpose is business intelligence, querying, and analysis, which includes visualization and dashboarding by your business analysts and end users using Amazon Redshift along with Amazon QuickSight or other partner ecosystem tools. Now the question is, how can you make such an architecture secure? And the answer is to start at the foundation and start with AWS Identity and Access Management. AWS IAM is the service that you would use to authenticate and authorize access to your AWS account and resources within it. Using AWS IAM, you can define users, groups, and roles, and you can author identity and access management policies that allow or deny access to specific AWS API actions. And because AWS IAM operates at the API action level, there are two important implications. First is that AWS IAM's reach extends into Amazon S3 and can be used to provide fine-grained permissions over Amazon S3 buckets and even objects within those buckets. That is possible because Amazon S3 is a fully managed service that is only exposed through AWS API actions. We can contrast that to Amazon EMR and Amazon Redshift. With both EMR and Redshift, AWS IAM controls only what happens outside your cluster. That includes things done to your cluster, such as cluster creation, modification, or deletion, and includes things done by your cluster, such as reading or writing data to Amazon S3 buckets. What happens inside your cluster is a totally different story, and such activity is controlled using EMR and Redshift's own internal authentication authorization mechanisms, which we are going to discuss later on in this session. Now, the second important implication is that it is absolutely crucial to understand each and every API action for Amazon S3, Amazon EMR, and Amazon Redshift. And that understanding is necessary in order to be able to author concise and least privileged identity and access management policies that closely match common activities that are performed in your enterprise data warehouse. Such activities include cluster management, for example, for Amazon EMR and Amazon Redshift, or just general administration of Amazon S3. Once we are done with understanding those API actions and putting together identity and access management policies, the next step would be to attach those policies to the users, groups, and roles of our enterprise data warehouse. In order to make such an effort manageable, you can design an access control matrix such as this one. On such an access control matrix, the different rows represent individual AWS identities, and the columns represent individual AWS services or resources. The intersection between a row and the column would be the list of identity and access management policies that must apply to that AWS identity and AWS resource. And because we will be applying combinations of IAM policies, it is a recommended practice that you leverage the AWS IAM policy simulator in order to verify that those combinations of policies yield the intended permissions. Now, for sensitive API actions, you would want to layer extra security controls in order to prevent malicious or accidental execution. And for that, you can use AWS IAM policy conditions in order to require multi-factor authentication to execute such sensitive APIs. When you enable MFA on a set of API actions, you would require that your AWS user has a virtual or a physical token at hand in order to be able to execute such actions. You can also use IAM policy conditions in order to specify further restrictions on such APIs, including, for example, a specific source IP address range or a specific time of the day. And just as you'd use AWS IAM to control access for users and groups within your account, you would also use AWS IAM to control the interactions between AWS services within your account. For example, for Amazon EMR, if you decide to enable debugging and logging for your cluster when you launch a cluster, that would require Amazon EMR to archive log files to Amazon S3, publish messages to Amazon SQS queues, and publish notifications to Amazon SNS topics. Now, for your convenience, these default permissions have been wrapped together or bundled under AWS Managed Identity and Access Management policies. Those policies are then attached to a pair of identity and access management roles, and those roles are then assumed by your Amazon EMR cluster and the Amazon EMR service. The recommendation here is that you make sure you understand those default permissions and tailor and customize a new set of permissions that matches the intended use of your cluster. Now, let us turn our attention to network security in the hybrid enterprise data warehouse. This architecture is similar to the one that I have shown you earlier, only with more networking details visible. On the right-hand side, there is your AWS environment, which in this case is a single virtual private cloud, or VPC. A VPC is just your private, logically isolated network within the AWS cloud. A VPC can be segmented into public subnets and private subnets. A public subnet is a subnet that has a direct network route to an internet gateway. An internet gateway is the access point through which traffic can cross from within your VPC out to the public internet and vice versa. A private subnet, on the other hand, is a subnet that does not have a direct route to an internet gateway. Instead, it has a direct network route to a virtual private gateway, or a VGW. The VGW is the access point through which traffic can cross from within your VPC to your on-premises networks and vice versa. Now, the question here is, how can we make our sensitive data flows secure in such an architecture? Ideally, we would want our network traffic to be encrypted. We would also want our network traffic to be private, never to traverse the public internet. And finally, we would want to be able to prevent unauthorized network traffic to unknown IP addresses and ports. Now, I'm going to talk about encryption in transit later on in this session. So for now, let us focus on network traffic privacy and authorization. An important step towards making your network traffic private is to launch both your Amazon EMR and Amazon Redshift in private VPC subnets with private IP addresses. Both services support doing so today, and doing so would render your clusters effectively inaccessible from the public internet. Another important step that you should take to make your data flows private is to set up and configure an S3 VPC endpoint. An S3 VPC endpoint is simply a point where traffic crossing from within your VPC to Amazon S3 and vice versa is private. It only traverses your VPC and the internal Amazon network. Now, to force all of the upload traffic from your on-premises network to Amazon S3 through that S3 VPC endpoint, that traffic would need to be proxied through a set of auto-scaling and load-balanced proxy instances within your VPC. That is necessary because VPCs today do not allow transitive routing. And once your data is in Amazon S3, we would want to ensure that data traffic between your clusters and Amazon S3 would go through that S3 VPC endpoint. And for Amazon EMR, that simply means properly configuring the cluster at cluster launch. For Amazon Redshift, that means enabling the enhanced VPC routing feature for your cluster. Interactions between your different user groups and your clusters would flow over the AWS Direct Connect, so those are private as well. But any traffic that is destined to a public AWS service endpoint must cross through the internet gateway. And for that to happen, we would need to set up a VPC net gateway in our public subnet. Now, that takes care of network traffic privacy. So now let's talk about network traffic authorization. And network traffic authorization is about applying rules on inbound and outbound traffic. Those rules might be based on a specific IP address range or a specific network protocol or specific ports. And there are three mechanisms that you can use to define and enforce network traffic rules. First, you can use VPC security groups to protect your Redshift and EMR clusters. In fact, Amazon EMR is protected, your Amazon EMR cluster is protected by default using a pair of security groups that you can customize. For Amazon Redshift, you can choose a security group that you already configured. The second mechanism that you can use is network access control lists. Network ACLs apply at the subnet level, and thus you can use those to protect your public and private subnets. The final mechanism that you can use is your own customer router or firewall at your end of the AWS Direct Connect. So just to sum up the benefits of this architecture, all of the data flows are private. You do not traverse the public internet. And there are a number of choke points where you can define and enforce network traffic rules. Also, traffic logging is possible with VPC flow logs. So you can log all traffic traversing your VPC and store those logs in S3 for further analysis. And finally, with such an architecture, dedicated tenancy is possible. And with dedicated tenancy, you would run your cluster nodes on hardware that is dedicated to you. Now, let us resume our discussion about access control. And in the architecture that I have shown you so far, there were just 3 teams. A team of data engineers producing data into the data warehouse, and 2 teams consuming data, a team of data scientists and a team of business analysts and end users. Now, we all know that reality is more complicated than that. What we often see instead is that there are multiple teams across different departments and different lines of business who would wish to consume data from the data warehouse. But not only consume data, they might also need to produce their own data sets and be able to share those with other teams. So in order to support this multiple team scenario, we need to achieve 2 access control objectives. The first objective is that every team must be able to get secure and segregated access to Amazon S3, Amazon EMR, and Amazon Redshift. And the second objective is that every team must be able to securely share their data with other teams. Now, there are 2 strategies that you can follow to that end. The first strategy is fine-grained data and resource ownership. Under such a strategy, a central data warehousing team owns and manages Amazon S3, Amazon EMR, and Amazon Redshift resources within a single account. Every team is then granted ownership of fractions of those resources. In Amazon Redshift, a team would own specific databases, schemas, or even tables. And in addition, they get their own share of their Amazon Redshift cluster using Redshift workload management. In Amazon EMR, a team would get access permission to specific Hadoop distributed file system paths, in addition to permissions for using specific Hadoop tools, in addition to their own share of the Amazon EMR cluster using Yarn job scheduling on Apache Hadoop. Now, because access is segregated with such a strategy, access segregated within Amazon EMR and within Amazon Redshift, access control is generally complicated to set up, maintain, and scale as your teams grow in size and number. Now, we can contrast that strategy to a strategy of coarse-grained data and resource ownership. Under such a strategy, every team is entitled to their own Amazon S3 buckets, in addition to their own Amazon EMR and Amazon Redshift clusters. A team's Amazon S3 buckets would contain data sets prepared for and by that team, and a team can securely share their data with teams in other accounts using AWS Identity and Access Management. Because team resource ownership is established by the AWS account, access control is generally simpler to set up, maintain, and scale as your team grows in size and number. Now, we talked a little bit about strategy, so let us talk about some access control specifics for Amazon S3. And here I would like to call out 3 important points. The first point pertains to team data sharing. So in a multiple team environment where teams share their data through Amazon S3, a team should be able to quickly and reliably answer the question of who has what access to my data. In order to do that, a team should consider centralizing the access control permissions to their Amazon S3 buckets in S3 bucket policies. An S3 bucket policy is just a usual identity and access management policy, only one that is attached to an Amazon S3 bucket rather than attached to a user or a group. The second point that I want to call out pertains to access control for Amazon EMR cluster users to Amazon S3. Your Amazon EMR cluster users have access to Amazon S3 through the cluster. And that is possible because of the default permissions attached to the EC2 default role that is assumed by your cluster nodes. So make sure to review those permissions to Amazon S3 and tighten them as necessary to grant least privilege access. The final point that I want to call out pertains to access control of Amazon Redshift users to Amazon S3. Amazon Redshift users would often want to copy data from Amazon S3 to Amazon Redshift and vice versa. In order to do that, they would use Redshift copy and unload commands. And for those commands to succeed, they need to run with proper permissions to Amazon S3 resources. Today, Amazon Redshift makes it possible to pass those required S3 permissions to your copy and unload commands using identity and access management roles rather than hard-coded AWS credentials. Now, moving on to Amazon EMR. Amazon EMR is a cluster management platform on top of which runs Apache Hadoop and Apache Spark. So in order to enable strong authentication and fine-grained authorization within Apache Hadoop, you need to configure Apache Hadoop in secure mode. When Apache Hadoop is configured in secure mode, Hadoop users and daemons are then required to authenticate themselves to one another through the Kerberos protocol and another Hadoop mechanism called delegation tokens. When you configure Hadoop in secure mode, Hadoop users and daemons are also granted permissions based on access control lists that you can configure in Hadoop cluster configuration files. Now, there are two important consequences for that. First is that you need to set up a dedicated Kerberos key distribution center for your clusters and properly configure Kerberos across your cluster nodes. And the second consequence is that as your Hadoop user base grows in size and number, manually managing Hadoop ACLs in cluster configuration files can quickly become unwieldy. And that is when you can leverage the help of open source frameworks that have been created to solve this problem, such as Apache Ranger and Apache Sentry. Now, moving on to access control within Amazon Redshift, it is much easier to set up in comparison with Apache Hadoop on Amazon EMR. And that is because Redshift is based on PostgreSQL. So you would find the familiar security controls that you would find in a relational database management system. This includes the ability to grant or revoke privileges on SQL activities such as insert, create, or delete. And those privileges apply also to specific Redshift objects, such as databases, schemas, tables, and user-defined functions. Now, that concludes our discussion of access control. Let us move on to see how you can protect the confidentiality and integrity of your data, both at rest and in transit, using encryption. And here, let us remember that we are talking about a data warehouse that supports multiple teams. And if every team is required to protect their data at rest using symmetric key encryption, it is not hard to imagine how those encryption keys can proliferate and get out of control. And that is why our first step to implementing encryption in the hybrid enterprise data warehouse is deciding on an encryption key management strategy. After that, we can proceed to pick an encryption mode for Amazon S3. We can then configure encryption on Amazon EMR, and then launch an encrypted Redshift cluster. And when it comes to your encryption key management strategy, there are a number of options to choose from. On the one hand, if you just want to ensure that your data is encrypted and you do not want to worry about managing the encryption keys yourself, you can just let Amazon S3 and Amazon Redshift do encryption key management on your behalf with minimal configuration. On the other hand, if you want total control on your keys, in addition to the ability to store those keys in dedicated hardware security modules, you can then choose to either use AWS Cloud HSM or use your own custom key management solution, either on premises or in AWS. Now, if your encryption key management needs lie in between those two ends of the spectrum, you should consider AWS Key Management Service. AWS Key Management Service, or KMS, is a managed service that simplifies creating and importing your own encryption keys, in addition to managing those keys throughout their life cycle. This includes rotating your keys, disabling or enabling your keys, deleting them, and auditing their use. KMS uses highly available hardware security modules behind the scene to protect your keys. And all three services, S3, EMR, and Redshift, can use KMS for key management. Now, with all these options, how can you make a decision? Here are three questions that you can answer as a starting point. The first question is, do I have to manage my encryption keys myself at all? The second question is, if I do have to manage my encryption keys, do I have to do that in dedicated hardware security modules? And the final question is, do I have to manage my encryption keys on premises? Of course, your situation might be more nuanced, but this is a good starting point. And based on your answers, you can decide on an encryption key management strategy. Moving on, the next step would be to configure encryption in Amazon S3. And this involves deciding on whether you want to do client-side encryption or server-side encryption. Client-side encryption is where you put your application in charge of the encryption process. Your data is encrypted, and then it is uploaded into Amazon S3. Server-side encryption is where you put Amazon S3 in charge of the encryption process. So you upload your unencrypted data into Amazon S3, and then it is encrypted right after it is uploaded. Now, the combination of client-side or server-side encryption plus your encryption key management strategy will yield the encryption mode that you should choose for Amazon S3. CSE stands for client-side encryption. SSE stands for server-side encryption. -KMS means that the master encryption keys are managed in KMS. And -C means that you manage your own master keys. Once we configure encryption Amazon S3, we can move on to configuring encryption Amazon EMR. And here it is helpful to understand how an EMR cluster stores and accesses data. An Amazon EMR cluster is composed of a master node that orchestrates a number of core nodes that store and process data. Every node in the cluster has storage that is split into two kinds of volumes, a root volume and one or more data volumes. The root volume is the volume from which your cluster node boots, and it also stores the Hadoop binaries. A data volume would contain things such as the Hadoop distributed file system blocks, in addition to the log files and the Hive Metastore database. Your Amazon EMR cluster is also capable of reading and writing data to Amazon S3 through the EMR file system client. The EMR file system client exposes Amazon S3 as a distributed file system to your entire cluster. The EMRFS client supports all encryption modes for Amazon S3 except server-side encryption with customer-provided keys. And all traffic in transit between the EMRFS client and Amazon S3 is encrypted by default in transit using TLS. Amazon EMR also supports local volume encryption using the Linux Unified Key Setup mechanism. Note that only data volumes can be encrypted. And for local volume encryption key management, Amazon EMR can integrate with either AWS KMS or use a custom key provider. When you enable local volume encryption, it also enables two Hadoop encryption in transit features. Those two features are encryption of RPC traffic between Hadoop daemons and encryption of HDFS block transfers. Now, you can specify all of these configuration settings today in a managed security configuration object. The benefit of using a managed security configuration object is that you can reuse your encryption settings across many Amazon EMR clusters, and that would help you to standardize your encryption settings across your hybrid enterprise data warehouse. Finally, moving on to encryption in Amazon Redshift, encryption at rest is an immutable setting of the cluster. And that simply means that if you launch an encrypted Redshift cluster, you cannot switch to unencrypted or vice versa. Once encryption is enabled for your Amazon Redshift cluster, all Redshift data blocks, in addition to system metadata and any backups or snapshots taken, are all encrypted. For encryption key management, Amazon Redshift supports integrating with AWS KMS or with a hardware security module. Finally, to wrap up our discussion about encryption, this is an overview of how you should implement encryption in transit in your hybrid enterprise data warehouse. Amazon S3 supports encryption in transit using SSL or TLS, so you should take advantage of that when uploading your data to Amazon S3 or downloading data from it. Amazon EMR can also write or use encryption in transit with Amazon S3 using or through the EMRFS client. And Amazon Redshift, by default, uses SSL for the Redshift copy and unload commands. For Amazon Redshift clients, you can enforce that clients connect over SSL, but to do that, you would need to enable the require SSL setting in your cluster configuration. For Amazon EMR clients, this is effectively Apache Hadoop clients. So for that, Hadoop Web UIs can support that you configure SSL, but for that, you need to consult the documentation for the individual Hadoop UI that you would like to use. This wraps up the first part of the session. So thank you for your attention, and I'd be happy to answer any questions after that. And Nate is going to share with you how hybrid enterprise data warehouse security is actually done.
Hey, everybody. I'm Nate Sammons. I'm a principal architect at NASDAQ, and let's get this going. Today I'm going to give a quick intro to who we are and what we're doing, and then I'm going to talk about the choices that we've made along our path to using Amazon Redshift and Amazon EMR for our data warehousing use. And then I'm going to talk a little bit about future directions for big data at NASDAQ. So first, if you haven't heard of us, most people know us as a stock exchange in the United States. We actually own and operate 33 different exchanges around the world, and we sell exchange software to over 100 different customers in 50 countries around the world as well. So first I'm going to talk about Redshift. Redshift has been in use at NASDAQ since it was in beta, and it's now our main data warehousing workhorse for all of our activities, at least in the United States. We daily ingest data from hundreds of different internal sources, and that's in the 6 to 20 billion rows a day range. The current footprint for that warehouse is an 18-node DS2 8x large cluster, and it stores just under 3 trillion rows. That's all highly sensitive data, so it's all the orders, trades, quotes, basically any message that crosses any of our exchanges gets into that warehouse for analytics and billing and that kind of thing. We also store membership information, which is used for billing, basically. So here's a graph of the last 18 months of data ingest every day in billions of rows. You can see that it's pretty sporadic, and it kind of tracks daily market volumes in general. But you can see there's like a gap at Thanksgiving and Christmas. It usually drops down, and then the beginning of the year, it kind of goes crazy again. So what are we doing with Redshift? First and foremost, billing and reporting is where it really all started for us. A few years ago, we rewrote the billing system on top of our equities exchange, and that involved porting it to Redshift. After we started to ingest all this data out of the equities exchange, it became really useful for a lot of other activities around the company. So as what's called a self-regulating organization with the SEC, we're required to police activity on our own exchange. So market surveillance is a real big part of what we do on Redshift, and that's looking for fraudulent or illegal trading activity and that sort of thing. We have a big economic research department, which does a lot of work on market structure and figuring out how we can use those 33 different markets to basically make more money. And then we have a trade history system called Trade Info that lets you log into a web UI and look at the status of orders from anything from ongoing orders today back several years. So those are kind of the main uses that we have right now. Let's talk about Redshift network security. So the main idea here is that we want to put Redshift into a very tightly sealed box, and we want to control all access to that database in or out. Right? So to that end, we run our clusters inside VPC subnets with lockdown security groups that limit the number of the set of IPs that are allowed to connect into those clusters. When Redshift talks to S3 to do copy or unload operations, it does so across a VPC endpoint to S3. We require SSL connectivity into those clusters, and we also assign individual SSL certificates to each cluster and then distribute those certificates to the various groups internally that need to actually connect to them. And then all of that data transfer is occurring over a AWS Direct Connect connection so that nothing traverses the public internet. And then furthermore, on-premise, we have a set of firewalls behind that Direct Connect connection, and those are also used to further limit activity. And now let's talk about the actual data security on those Redshift clusters. So we use on-premise HSMs to store the master encryption keys for those Redshift clusters. We also operate Redshift with a minimal IAM policy that basically says that it can read and write from particular S3 buckets and really do very little else. We encrypt all the data that we write into S3 using client-side encryption, and that's opposed to server-side encryption, so that we make sure that all the encryption operations are happening either on-premise or they're operating in EC2 instances that we're in control of. We use a custom key management system that stores all of our encryption keys on-premise in a database, and then they're also rooted in that on-premise HSM as well. I talked about key management, right? So we've chosen to use on-premise HSMs for our activity, and that does give us a physical separation of the keys, right? I can sever that direct connect connection and terminate the Redshift cluster, and then all that data is completely useless to anyone who doesn't have physical access to our HSMs. It does require you to use an EIP on your Redshift cluster, and the reason there is that when you pair something with an HSM, there's a certificate exchange, and it involves the actual IP address of the client for the HSM. And then if you were to reconstitute that Redshift cluster on other hardware, it's obviously going to have a different IP address, but using an EIP, it's able to talk back to that HSM again. But it's really important to note that HSMs are really delicate hardware devices, and they require a lot of special handling. So unless you really need to use them, I would recommend against it. But that's something that you're going to have to figure out for each of your own organizations. In contrast, the Amazon KMS gives you policy-based key rotation, gives you IAM policy governing all the usage of those keys. It gives you, detailed CloudTrail access logs for every kind of encrypt and decrypt operation, and you get high durability storage. So in our case, we have a number of different HSMs in different geographic locations, but it's important to note that if you have all your keys in one HSM, that's where all your keys are, right? So you literally have your eggs in that basket, right? And the other nice thing about the Amazon KMS is it supports other Amazon services like EBS and other RDS databases and that sort of thing. But you do need to trust Amazon, right? So you need to figure out for your organization where you lie on that spectrum of trust versus not trust, basically. And that's a big decision that you're going to have to make for yourselves. For access control and monitoring, we maintain very tight control over who's allowed to write into that Redshift database, and that's mostly because we have a lot of regulatory reasons for keeping that data, and we also just don't want to accidentally delete anything. Users are granted access to specific schemas and specific tables for whatever it is that they need to do, and we also grant them a specific set of workload management resource constraints, right? So they only get a certain slice of the cluster's CPU and memory, because you don't want any one group to be able to completely paralyze the cluster by running crazy queries and that kind of thing. After that, we also pull all the logs out of S3 down onto on-premise for analysis, and that includes Redshift activity logs, which is connect and disconnect, all the DDL operations, all that kind of thing. We pull down CloudTrail API logs and VPC flow logs. And then we also monitor a connection or a table inside Redshift called STL connection log, which is just a live log of all the connections to the database, so that we can figure out if we know who's connecting to what database. For managing Redshift clusters, we used to not delete anything, right? Because nobody wants to delete data. That kind of led us to growing those clusters once per quarter. And that is actually not all that sustainable. So One of the reasons we've switched to keeping a 1-year rolling window of data in Redshift is that old data is really accessed very infrequently, right? So it doesn't make a lot of sense to spend money on live CPUs and spinning disk attached to your cluster for data that you're not going to look at, right? So now we resize those clusters, you know, basically as market volumes increase and as we have acquisitions. So we recently bought a company called the ISE, and all of their data is going to end up in Redshift, so we're going to have to expand this cluster actually pretty substantially. But the other reason is that resizing a Redshift cluster is really not an instantaneous operation, especially if you have a couple hundred terabytes of data that it has to rebalance. It's become much, much, much faster over the last few years, but it's still something that you need to plan for your operations group and that sort of thing. So for all those reasons, we've extended our warehouse into EMR and S3. And that's what I'm going to talk about next. So EMR and NASDAQ is gaining a lot of traction internally. We're building basically an open data platform on top of S3 where we parallel load data in every day to Redshift and to EMR. And when I say we're loading data into EMR, what I really mean is that we're producing encrypted Parquet files and we're storing those in S3. And in that case, we're keeping the data forever, or as long as we can, humanly possibly keep it. The current footprint there is about 5.1 million objects and about 500 terabytes. And that's approximately 6.5 trillion rows since the beginning of 2014. Internally, we actually have a data archive of all the transactions on our exchanges dating back to the mid-1990s. And we're in the process of moving all of that data into S3 as well. And that's around 1.5 petabytes of data. Again, because nobody wants to delete anything. So I talked about Parquet. We actually evaluated both Parquet and ORC files, and we arrived at using Parquet. It's a modern columnar format with good data compression. It's a columnar format, right? So you get better data compression with adjacent columns or adjacent values for a column. It's a self-describing format. And what I mean by that is that I can take any random Parquet file, crack it open, and I can examine the data structure that's inside, right? I can figure out the name of the table, the name of all the columns, their types, all that kind of thing. And if you use CSV files or whatever, you can't, you have to interpret what kind of data is in there. The other nice thing is it has a really growing support in a lot of different open source communities. And for our two main use cases, Spark and Presto, it works very well. And then finally, it has good encryption, or a good performance while encrypted, which for us is really a deal breaker because we have to encrypt everything that we store in S3. So what are the workloads that we're running on EMR? Like I said, we have basically Spark and Presto. On Spark, we're running Zeppelin, which is a nice notebook interface on top of it. Economic research has been using Spark like crazy. Market surveillance is starting to evaluate Spark with some of the machine learning technologies there. And we also have a dedicated machine learning group that is doing a lot of experimentation with derivative data sets and sentiment analysis and all that kind of thing. They're all using Spark and Zeppelin. Presto is a SQL interface on top of data, which was originally written by Facebook, and they open sourced it a few years ago. That system is used by our trade history system called Trade Info. So if you query for an order that's 6 months old, it's going to hit Redshift. And if you query for an order that's over a year old, it's going to hit Presto. And then finally, we're also experimenting with business intelligence and reporting activities on top of Presto as well. And it's actually going really well. It's a great system. So it's important to talk about our data strategy for EMR. So with Redshift, you have CPU, memory, and disk coupled together on each node, right? And if you expand your cluster, you're expanding your storage and your compute and your memory all at the same time. With EMR and our strategy of using S3, we're able to scale those two independently, right? I don't even need any CPU. For instance, on the weekends, I don't have to run anything. But I can keep expanding that data footprint in S3 basically infinitely. We use a Hive directory structure on top of our data in S3. Basically, all of our data is time series, right? We get orders every day. They're all time-stamped to a nanosecond precision. And this directory structure lends itself really well to partitioning data by date. So the directory structure in S3 is basically The schema is the first directory, and then the table is the next directory, and then there's a partition, and then there's a bunch of Parquet files, right? That also lends itself well to fine-grained access control using bucket policies, because I can grant access to a specific subset of directories for a particular user or a particular group of users, that kind of thing. It all works very well. And then the other nice thing is that we can use, S3 is really our source of truth, right? So if our Hive metastore were to be corrupted or destroyed somehow, we can always recreate all of that information by just looking at the files in S3. And you can use the Hive msck repair table command, and it'll figure out all the partitions for a given table again, just by crawling S3, basically. So we use a multi-account strategy with S3 and EMR as well. And this lets us do a lot of nice things. So we have a centralized account where we store all of the actual data, and then we have a metastore there that we update every day as we're adding new partitions to that data, right? This lets, and then individual applications or internal departments have their own Amazon account, and they get their own bill. So if economic research, for instance, wants to run a ton of CPU on something, they can do that, and they're not going to compete with CPUs for the trade info system, for instance. So it's really clean. It lets them run whatever they want. We've never really had a contention issue with S3 as well, because it scales extremely well. Like I said, we use cross-account bucket policies to grant access to these different groups, and then we use VPC peering for Hive metastore connection, right? Because there's a thrift pipeline basically that goes from the customer EMR cluster over to the Hive metastore cluster. So for network security, this looks very similar to the Redshift setup. We run our clusters in private VPC subnets. We use a VPC endpoint for talking to S3, and we lock down security groups. If the EMR cluster needs to talk to other Amazon APIs that aren't S3, that has to go through a NAT gateway that's in a public VPC subnet. We can monitor all the access and security groups across all of this to keep very tight control over everything. And again, accessing these clusters from on-premise is done across a VPC or a Amazon Direct Connect, so that nothing really traverses the public internet. And again, on-premise firewalls to further limit connectivity. So for data security, these clusters are not long-running, other than the Hive metastore, which runs all the time, but it doesn't actually store any data. So we use HDFS only for scratch space. All the permanent data is stored in S3. It's a lot cheaper anyway. On the actual instances, we've started to use the new EMR security configurations, which allow us to encrypt the local disks, or the data volumes at least on those local disks for scratch space and that kind of thing. And we also have an EMR bootstrap action that configures SE Linux on each of the nodes in the cluster. And that script in particular is kind of special in that it has to reboot the entire cluster when you start it up. So you have to basically wait for the cluster to end up in the waiting state, and then you reboot everything, and everybody comes back just fine. For data security on EMR, we use EMRFS, which is an HDFS interface on top of S3. That has client-side encryption built in as part of EMRFS, so it's actually very easy to use. We use a custom key management system, so we have a custom encryption materials provider jar that we place in S3, and then it gets copied down on each cluster node. And then it's also really important that requests to seek within an object in S3 work even though it's encrypted. And that's really important for all these modern file formats like Parquet, because they have an internal block structure, and that you have to seek around within the file and not just read it sequentially from the beginning. And then again, we're using bucket policies for multi-account access. So for Spark data security, EMRFS just works. You basically do a couple configurations on EMR, and it's off to the races. It was very easy to get going. For Apache Zeppelin notebook storage in S3, we actually contributed to that project to allow custom KMS and Amazon KMS for client-side encryption of the notebooks that are stored in S3. So as of version 0.6.0 of Zeppelin, you can just set up configurations to make that go. If you want to look at the GitHub pull request, you can see it wasn't all that much work. And then for Presto, Presto doesn't use EMRFS. It has its own S3 file system called Presto S3 file system. And that's part of what Presto calls the Hive connector, which allows you to talk to a Hive metastore for metadata and then talk to S3 for your actual data. So NASDAQ contributed client-side encryption support for Presto. As of version 0.129, which was a while ago, in Presto terms anyway, we contributed client-side support with, or client-side encryption support with custom KMS. And then for version 153, we contributed client-side encryption support with the Amazon KMS as your key management system. And you can, again, look at those pull requests if you want to see what happened there. And then finally, the next thing that we're working on is we have all these groups that are producing data sets for their own use in their own accounts. But in some cases, those data sets are broadly useful to the rest of the organization. So we wanted to figure out a way to let those groups share that data with the overall organization, but still maintain very tight control over who's writing to this archive, right? I don't want to just give out S3 write access to anybody in that bucket because bad things could happen. So what happens now is clients can perform analytics in their own account using whatever tools they want, Spark, Presto, Drill, like anything they feel like. New data sets are created in that account and placed into a staging bucket where we, the centralized warehouse account, we receive SQS messages notifying us that there's a new file in that staging bucket. And then we can examine that file, figure out where it's supposed to go, and then place it at the correct location in the main archive. So this is nice because it allows all of these customer accounts to do whatever they want and produce these data sets in any way they feel like. And then we can still maintain tight control over how the entire archive is managed. So that's all I have. Thank you very much for your time. And remember to do your evaluations. And I think we're going to take questions if you like. So thank you.
Thank you.